The BAGS interactive animation system is a system for generating real-time, user-controlled, and batch animations. BAGS is designed to be both a powerful research testbed and an integrated set of modeling, simulation, animation, and rendering programs to be used by scientists, engineers, and artists. BAGS represents four-dimensional models with a distributed, object-oriented database that allows a close integration of a variety of interactive animation techniques. The user's interface to the database can have multiple views specialized to the tasks at hand. Now we are looking at the three-dimensional view of our interactive modeling and animation system. The model is being rendered using a radiosity technique. The white cube near the ceiling provides the light in the room. We are seeing the lighting improve as the renderer iteratively refines its solution on a remote machine. When an iteration is done, the radiosity client updates the shading of the model and informs the database that a change has occurred. The database is then responsible for informing interested clients of that change. BAGS supports other clients as well in order to present the user with a variety of ways to visualize and interact with the model. Here we see another such client, the tree hierarchy editor, which provides editable views of the inherent structural aspects of the model. Each window contains a tree representing the modeling hierarchy of a different object. The user is selecting objects from the hierarchy in each window in order to create a new group. Once the user types in a name for the group, a window appears containing the tree for the new group. This tree editing client also supports interactive detail elision so that users can focus on the part of the model that they are interested in. Let's return to the three-dimensional view. Now we add a gray tablecloth, simulated by a finite element mesh. You can see how it drapes across the radiosity rendered table, demonstrating how multiple simulation techniques work together. Next, another simulated object joins the scene. This blue robot's single arm is controlled using our iterative inverse kinematics algorithm, which operates in linear time and supports joint limits and weighting. The user interactively specifies a goal object, shown as a yellow cube, which the robot tries to reach for with its hand. Now we bring in a second robot. Each robot will pull on one corner of the cloth, again demonstrating how independent simulators interact in BAGS. This is achieved by constraining the corners of the cloth to the robot's hands. When the goal objects are moved, the robot arms move, and the cloth remains attached to the hands. The cloth constraints can also be turned on and off interactively, causing the cloth to react appropriately. The BAGS database design allows each of these robots to be manipulated by different users from different client programs. When a value changes in a given client, the database is notified, and it then updates all affected clients. Since the database stores a full four-dimensional description of a model, clients can be written to control time-varying aspects of an object. Here are two such clients, sliders and graphs. Each of these is running on a separate machine and outputting to the same X display. Notice that as one client is interactively manipulated, the other automatically updates as well. At the top of the screen, we see the slider animation editor. It represents control points in animations as icons along a horizontal time axis. The sliders allow users to easily edit the timing aspects of an animation by dragging icons along the time axis. Below the sliders is the graph editor, which displays how parameters in the animation are interpolated over time. Here we see graphs for 3 parameters in an animation. The upper two graphs are actually different components of the same change operator, so that when the time of a control point in the upper graph changes, the middle graph will automatically update. The database also supports more specialized clients, such as this spline editor. This editor has specialized capabilities, such as bias, tension, and knot vectors, that would only complicate a more general client. Now we return to our three-dimensional view and add an object of revolution, a vase, created from the spline path we just saw. This spline path, shown to the right of the vase, is itself composed of point objects. Thus, when any point object changes, the path is updated to show its new configuration. The object of revolution is in turn updated when the path changes. These dependencies are pre-computed so that minimal updating is required. Now we would like to be able to place our revolve object on the radiosity rendered table. Using BAGS' powerful three-dimensional interaction techniques, we select the vase and position it using its handles so that we can see the bottom more clearly. We choose a resting point for the vase, giving us a coordinate system aligned with the surface normal. Next, we pick where to put the vase, giving us a second coordinate system. The vase then snaps from the immediate foreground to the table, with the two coordinate systems aligned so that the objects are tangent. It can also be snapped to any other object in the room. As a final touch to our scene, we will add some scenery outside of the window. This scenery is actually a pattern-mapped cube which we can manipulate as easily as any other object. We move it to the wall resize it, and put it outside the window. The bag's interactive system provides a powerful research testbed that allows integration of many different modeling, animation, and rendering methods. Further, the object-oriented nature of the database allows new algorithms to be rapidly prototyped. A new method can quickly talk to the database and have the full resources of a solid modeler, a spline editor, gestural animation controls, and a host of dynamics and simulation methods. Most importantly, this allows us to focus our research on new four-dimensional modeling techniques without having to continually rewrite previous code. DART is an interactive distributed ray tracer that lets the user select regions of an image to be progressively refined. Here we have an image of an android rendered using DART. This is a wireframe version of our android. This crude image takes only a few seconds to bring up, but now we can select very specific regions that we wish to see ray traced. The progressive refinement algorithm shoots one ray per pixel, performing many passes. At each pass, the resolution increases with a corresponding decrease in block size. Once the size of the blocks are the size of 1 pixel, DART begins to adaptively supersample the image to provide anti-aliasing and smoothing of the distributed effects that DART supports: focusing, penumbras, glossiness, translucency, and motion blur. DART gives the user the power to refine just that which is needed. We've found that this simple idea can save the artist hours of rendering time and human time.